So next, let's talk about the total derivatives. So the things we talked about before is called total differentials, right? Total differentials. And here we talk about the rules of differentials. Now, total derivative is another thing, but it's really closely related to total differentials. So for total differentials, we called this as dy, right? So the change of y, given the very small change of y, right? Given a very small change of all the variables, it's called dy. So dy is called total differentials. But total derivatives means dy over dx, for example. Right, so this is the total change, although the change is very little, the total change of y with respect to the change of x. Right, so here this is called total differentials. So here this is called the total derivatives of y with respect to x. So here y is a function of, for example, y is a function of x, z, and w, right? So if y is a function of x, if we have only one variable x in the function, so dy over dx is also the partial derivative, right? Because there's no other variables. So dy over dx is the same as partial y over partial x, right? So if y is a function of three variables, x, z, and w, so we have two things, and the two things are different. The partial y over partial x is now different. It's not equal to dy over dx, right? So partial y over partial x is the change of y with respect to the change of x. But all the other variables, z and w, do not change, right? So this is the definition of partial derivative of y with respect to x. But because y is a function of three variables, x, z, and w, so partial y over partial x is not the same as dy over dx. Right. So dy over dx is the total derivative of y with respect to x. Right. So dy is a total differentials. So here it's not the same. Right. So in dy over dx, we don't control the other variables to stay the same. So z and w may also change. Right. The reason that z and w may also change is because maybe when x changes, z and w also change. Right. So maybe z is related. Maybe x is related to z and w. They are not that independent as before. Right. If they're totally independent, then we can calculate the partial y over partial x very easily. But now if the three variables are related to each other, so sometimes we use the total derivatives to represent the change of x, give the change of y given the change of x. Right? So that's the difference between these two. If y is a function of three variables, and the three variables may relate to each other, so we calculate the dy over dx for most of the time instead of the partial y over partial x. But again, we can still calculate partial y over partial x, right? But that means that they have different meanings. So dy over dx means the change of y given the change of x, but all the other variables may also change. But partial y over partial x means all the other variables do not change. And what's the change of y given the change of x? So these two things are different in a multivariable case, but they are different in a single variable case, right? Because there's no other variable. So the partial derivative is just the same as the total derivative here, right? So here in the section 3, we talk about the total derivatives. And I'll show you how to find out the total derivative, how to calculate that, right? So suppose we have a function y equals to f x w, but x and w are related to each other, right? So they are not independent, right, to each other. So we can use a function g to represent the relation between x and w. So x is a function of w. X equals to g of w, right? So x and w, the two variables, they're related to each other. Okay, so we can use another function, another composite function to represent this. And so we can incorporate the function g into the function of f. So y becomes f of gw and w, right? So gw is just x, but we replace x using the function g of w. So here y is just in this representation, y is just a function of w, right? gw and w. So we can get rid of the x. So the reason we can get rid of the x is that we are interested in the relationship between y and w, right? So that's why we write this in this way. So for the variable w, it can affect y both directly and indirectly, right? The direct way to affect y is through this, right? Because y is directly related to w in this function. It indirectly means that the w variable can first affect x, and x can affect y, right? So w first affect x, and then x can affect y. So this is an indirect way of the relationship between w and y. But w is also a direct function. W is also a variable in function f, so it can also directly affect y. So if we have this kind of relation between the two variables, the two variables are related to each other. And suppose in this case, we want to find out the total derivative of y with respect to w. So it's this thing, right? dy over dw. So we can find the dy over dw in two ways. So this is the first way, right? The second way is easier. I'll talk about that here. The second way is to first write down the total differential function, right? Remember the total differential function? Okay, already here. It should be, so dy is y is a function of x and w. So this should be f, right? X and the dx plus fw dw. So fx is the partial derivative of y with respect to x, and fw is a partial derivative of y with respect to w, right? So we first write down the total differential function like this, and then we divide dw on both sides. So this becomes dy over dw equals to fx dx over dw, right? So this is just a fw because we cancel the dw, right? We divide dw on both sides. So this is one easy way for us to find out the total derivatives, right? The second one is just if you know this function, we can just plug in here, right? dy over dw is fx times dx over dw times fw. Right, so if you are really familiar with the formulas, then you can get rid of writing down the total differentials, right? You can just write down this. So fx is partial y over partial x, and then fw is partial y over partial w. right? So from this equation, we can note that there are two ways to affect the total derivative, right? The first here, fw is a direct way, right? Because w is in the function f, so it can directly affect the total derivative. And the second is to first through x and then through the function f, right? So there are two ways for w to affect y, and you can reflect in this function here, in this formula here. So this is just the way we find out the total derivative of y given the variable w, right? So let's look at an example here. So y is a function f of x and w is 3x minus w squared. But x is also a function of w, right? So all of them are related to each other. So x equals to 2w squared plus w plus 4. And our job is to find the total derivative of y over with respect to w, right? Okay, so the total derivative should be partial y over partial x, which is 3, right? So here this partial y over partial x times dx over dw, dx over dw, which is 4w plus 1, right? We take the derivative of x with respect to w. And then plus partial y over partial w. We consider x as a constant now, right? So this is just a minus 2 times w. Just pay attention that when we calculate partial y over partial w, we consider x as a constant in the function. Although x is a function of w, but when we calculate the partial y over partial w, we just get rid of x, or we just consider x as a constant, right? We don't just plug in the x and then calculate, right? That's wrong. So as we said, the partial derivative here, as the total derivative here, the partial derivative does not control the other variables to be the same, right? So actually the other variables can still change. But for the partial derivatives, all the other variables should stay the same, right? So that's a difference. And so that's a difference in calculating total and the partial derivatives. Okay. And then, so this is a variation. So let's look at a more complicated case with y equals to f, x1, x2, and w. And both x1 and x2 are functions of w, right? So x1 equals to g of w and x2 equals to h of w. And then, again, the variable w can affect y. First is indirectly via the function g, and then indirectly via the function h, and then directly for the function f. Right. So in this case, again, there are two ways to find out the total derivative. The first is to write down this directly, right? The second is to write down the total differentials, right? dy. Write down the differentials, and then we divide dw on both sides. But in either way, you can find this function, right? You can find this formula in the end. So the total derivative of y with respect to w should be equal to, first, the indirect way of w to affect y, right? So w first affected x1, and then x1 can affect y, right? So this is the first way to affect y. And the second, w can first affect x2, and then x2 is in a variable of function f, so x2 can affect y through function f. Right? So this is a second indirect way. And the last way is the direct way. So w is in the function f, so it could directly affect y, right? So if we know how many ways the w can affect y, you can still write out the formula like this, right? You don't need to write down dy as a long equation and then divide the dw on both sides. If you know how w can affect y, you can write down this at once, right? You don't need to write down the dy thing. So there are 3 ways. So as I said, when w changes, both x1 and x2 will change, right? So the change of y given this kind of change of w is called total derivative. But for partial derivatives, we just think of x1 and x2 as constants, right? When we take the partial derivative of y over partial w, right? So we don't assume x1 and x2 to change when we calculate the partial derivative. But for total derivative, it's a little bit more complicated because all the other variables, they are interrelated. So they can change too. So we'll write out a longer formula to find out the total derivative. So partial y over partial x1, we call that f1, right, for simplification. And the partial y over partial x2, we call that f2. And then this is fw, right? So the calculation is the same from here, right? We just find out the total derivative of x1 over dw and times the partial derivative, right? So here we can write dx1 over dw, but not partial x1 over partial w, is because x1 is a function of only w, right? x1 is a function, x1 and w are related through the function g. And x1 has only one variable that can affect, so it's w. So there are no other variables that can affect x1 except besides w, right? So that's why the partial derivative of x1 with respect to w is just the same as the total differentials. So we can write the dx1 over dw here because x1 is just the function of only w. And again, x2 is a function of w, and there's only one variable, which is w. So we use the dx2 over dw here. And then the third one is fw. And pay attention that when we calculate the partial y over partial w, it's not a total derivative. So don't plug in g function and h function in the f function and then calculate the partial derivative of w, right? Because this is a partial derivative, not total derivative. Partial derivative of partial y over partial w, when we calculate this thing, we just consider x1 and x2 as constants, right? Although they are functions of although they are functions of w, but when we calculate the partial y over partial w, we don't plug in the g and h functions, right? We just consider x1 and x2 as constants, and then we take the derivative of y with respect to w, right? Because this is a definition of partial derivative. We just control all the other variables to be the same. So consider that they are constants. So this is a partial derivative of w, right?